Alright, what we are going to do today is we are going to learn about the compressibility factor. The compressibility factor is used so that we will be able to solve. It's used in the cubic function of the equation of state equation, and it helps us solve for either pressure, specific volume, or specific temperature when dealing with our critical temperatures and critical pressures and critical volumes. It really helps us in the long run of complicated equations, and I'm just going to explain what the compressibility factor is and how it's going to work for our equation of state. So we know that equation of state is used to find specific volumes, but we also learned that with the van der Waals equation, it is more, how would I say, it's not simplistic, as I would say. So we know that it is equal to P equals R T over our specific volume minus B minus our constant of a constant plus of B multiplied by our specific volume plus sigma of B. And that is our equation of state. But what we're trying to do is incorporate our compressibility factor into our equation. And our compressibility factor is Z, and Z is equal to R. Z is equal to PV over RT. And so what we need to do is we need to figure out how to put Z into our equation of state equation. And I know it sounds kind of easy, but it is actually more harder than it may seem. So what we're going to do first is we're just going to look at one side of the equation first. We're going to look at P equals RT over V minus B. And what we can do from here is, when we look at Z, it's PV over RT. And when we look at our initial of our equation of state, RT is on top. So we know in the beginning we need to get rid of the RT on top and find a way to put our pressure up there. So what we're going to do is we're going to multiply by P over RT over P over RT to the top and bottom. That is going to give us P equals P over pressure times our specific volume over RT minus B P over RT. Alright, and now once we've done that, what we can do is we need to worry about the other side and see how we can get that into terms of Z as well. So we have A over our specific volume plus epsilon of B multiplied by our specific volume of sigma B. So what we're going to do here is we are actually going to, let's see how we would do that. Well, we already have PV, RT. What we want to do is we want to find a way to get A in terms of Z. So I guess how we would do that is we're going to actually, oops, didn't mean to do that. What we're going to do is we're going to multiply our right side of that equation by PRT again. I feel like that would help. So we're going to get minus PA over RT over V over RT plus V P over RT. And that's just top and bottom times V plus sigma of B. And so you notice that we have another volume that's accounted for. We're going to have to multiply our top and bottom again all over P over RT. So let's do that one more time so that we can get our final equation of P is going to equal, this is not working. P is going to equal P over PV RT minus B P over RT minus P squared A over R squared T squared over multiplied by PV over RT plus sigma B of RT. Now, once we're here, what we don't have is V anywhere, do we? No, not at all. So we're going to have to go into our equation and multiply V across the entire top. So let me get rid of this real quick. And now what we have is we have P equals to P over PV of RT times our B constant RT of P squared R squared T squared over our bottom over our bottom. Now we need to multiply everything by V over RT so that we can get a compressibility factor on the top and bottom of many of our equations. We're actually going to do this at both sides. So V over RT and V over RT. And since we know that Z, our compressibility factor, is equal to PV over RT, I'm going to rewrite that over here as Z equals Z, because this right here, multiply by that right there, over, we already have a PV RT on the bottom right here, so Z, and we're going to subtract that by, we're going to make B equal to our constant of P over RT. So minus B. Oops. How do I? Nope. Make sure everything's checked on OBS. Okay, perfect. Just want to make sure. And now we have, no. Now we're going to subtract since we times by a V of RT on top, we get to take away and we get a Z, but that's still multiplied by a P. We get a Z because we get 1P, but we still have a P over RT squared. Yeah, RT squared. Just want to make sure. R squared, T squared. This is one long equation of A over, so 1P goes away. Wow, that's a big help. And we have on the bottom PV over RT, so we see that one. Z plus we know that our B constant times P over RT is already equal to B, so I'm going to write epsilon B again, multiplied by a Z plus there is no pressure in that one. Why is there no pressure in that one? Didn't we multiply by PV RT? Yeah, we're missing the P in this right here. So that is also going to be a sigma of beta. So here's our new equation. We have Z equal to Z minus B of our compressibility factor. And this is important for our equation because compressibility factor, once found, will help us find our specific volumes. We know our critical temperature and critical pressure because our B and A can be found by taking the roots of our critical values. So that is one side of the equation out of the way. And if we know our T and P, we can find our specific volume, or we know our specific volume and temperature, we can find our pressure, and vice versa. So it makes one giant complicated problem a real simple solution. It's just the process to get there isn't as easy as that would. So this is where we're at. And what we need to do from here is we need to figure out how to make this into an equation that's actually going to work for us. And at the moment, I don't see it working for us, you know? It's so complicated. We have our compressibility factor everywhere. So let me rewrite everything and let me try to get it in terms that are going to be more simpler for us to actually use to solve for our compressibility factor and for our equation. I like this tool. Try to fly. I'm gonna put you right there. We're gonna get a new color, and we're going to actually divide everything by Z. So what we will get is 1 is equal to 1 over Z minus B beta, which is going to be subtracted by Z divided by Z is going to be 1. And we still have we still have this. But what we know is that beta is equal to B times our pressure divided by RT. So who's to say that we can't have a Q equal to A over B RT? And what you'll find is that BQ will be equal to A times B of P over B R T squared, which is actually our B will cancel, and then we have PA RT squared. So now we're going to have minus Q of beta over Z plus epsilon B times Z plus sigma B. And this is going to be actually the end to our equation. So once we have our compressibility factor, let me clear the screen so you can see what it is clearly. We will be able to use this for our equation. And it might not seem like it, but we know that it's equal to 1. And if we find our compressibility factor, we know that Z is equal to PV over RT. So let's say we're trying to find our specific volume. That means Z times RT over P is going to be the specific volume. So if we can find just our temperature and pressure, and we know our compressibility factor, and we know our critical temperatures, and we know our roots, we'll be able to find our volume at a specific volume. I hope that was useful for you all. I really hope I explained that well. If not, just let me know. Thank you so much.